I can't tell if I'm live. Am I live? I think I am. Okay. All right, so I'll start now. No. Arden, can you confirm that I am live? Am I live? Am I live? I stopped hearing you. Can you hear me? All right, let me try something. Can you hear me now? Talk deaf. All right, so I won't see you, so I'm not sure how you're going to communicate with me. Here. All right, great. All right, so I'm going to get started. Just in case that's my number. All right, so now let's start. And I don't know if you started recording yet. I apologize for the technical difficulty. For some reason, I have lost the audio with the AV guide. All right, hi, I'm Jerry Seidman. I've been asked by Arden to give this lunchtime talk on a topic that I've been working on and focusing on a lot for the last year or so. A little bit about myself. I have a long history in distributed systems. I designed a lot of software, some of which you use every day. If you ever send a text message, it's going through software I designed. System that's doing 10 billion transactions a day. So I'm kind of very comfortable with fault tolerant, low latency, resilient systems. I was very interested in Kubernetes early on, and I've been working with Kubernetes for a long time and Docker containers. I am a lecturer for Arden. I've given several classes on containers and Kubernetes and related topics. And I'm also president at Orastor, which I'll talk a little bit about that later. But this talk is about how do you speed up cold start times dramatically for any AI, ML, or basically any large container. There's nothing specific about AI or ML containers. For example, SAS, the statistical package is a 40 gigabyte container image if you're a company that runs that. So I'm going to cover a lot of stuff, but we're going to go through a journey from, what actually are the problems that containers are solving. We're going to talk about software deployment in general, issues when deploying containers at software at enterprise scale. We're going to look at how container runtimes work. We're going to spend a lot of time kind of going into the guts of how container runtimes work, in particular with how they set up their file systems. And we're going to about overlay FS, and I'll give a whole bunch of demos. I think I have like 12 demos, so it's going to be a demo-rich talk. So what actually is the problem that containers are solving? It's actually solving a few problems. One is, yes, it's a lightweight VM that produces reproducible runtime environment. Namely, when you're running a container, as far as that container is concerned, it owns it has its own machine with its own network and its own memory that's sandboxed from any other container running on that machine. That's similar to what VMs do, except unlike with VMs, containers share a single host operating system, but with VMs, each VM has its own its own copy of the operating system. What I want to focus on today is the other aspect of what the problem that containers solve, and that's one of software deployment. We create or somebody else creates a containerized application. It sits up in some container registry, and we deploy our application by just saying, Docker run and, docker.io/nginx, and all of a sudden we have an instance of nginx running on our system. And it was deployed onto our system from the container registry, downloaded onto our local machine. Namely, when we cold start an application, when we first time run a containerized application, the container image must be pulled onto your node, whether it's your desktop or a compute node or a Kubernetes node, before that container can start. The next time it can reuse that downloaded image, as long as it hasn't been garbage collected. And I'm not going to talk about how container runtimes do garbage collection, but if any of you are new to containers, what you're going to find very quickly is that your disk is going to be full very fast. So you really have to understand what's happening when you run containers and download images. Kubernetes solves a different problem. Kubernetes is solving the problem of resource allocation across clusters. Namely, I've got N jobs, I've got M computers. How do I figure out which ones to run them on? And it works by a scheduler that looks at the resources that are currently being used, CPU level, memory, etc., disk, and allocates jobs. So it uses containers, but it implicitly is not a container technology. In fact, people are doing things with things other than Docker containers being distributed by Kubernetes, entire virtual machines, and WASM, if you're familiar with WASM. So, okay, so again, why do we want these lightweight VMs? We want to have a single machine, a single node or desktop running many logical computers that are sandboxed and isolated in terms of disk, memory, CPU. But there's other things on the OS level that are important. That's not sort of the resource level, but on the OS level, things like user IDs and group IDs are important. Like if you ever ran something as root, your user ID 0. How can I have multiple machines, multiple logical machines on a computer running in a sandboxed way and sharing root? And the answer is there's something called namespaces, and we'll talk a little bit about that, that allow you to segregate these. So there's a whole, each container has its own block of user IDs and group IDs, but it's presented to the container as if it's yours. It has their own process IDs, because if I can see the process IDs of another container, I could kill processes, for example. And the value of these lightweight VMs, namely containers, is they use less disk space and memory. They start faster once they're downloaded. And with Kubernetes, you don't need VMs at all. I know a lot of organizations that are just running Kubernetes on bare metal. So let's ask a more broad question, focusing on software deployment. So what is software deployment? And it's just the process of getting a bunch of files onto a machine. Duh, right? That's what software deployment is. It's an old problem. We've been deploying software for 50 plus years. You know, paper tapes, cars, reel-to-reel, mag tapes, floppy disks, CDs, DVDs. Goes back a long history. It's all about how do I get files onto a system. Obviously, more recently, we distribute zip files and tar files and tar.gz files. But realistically, we don't want that, because deploying software is a little bit more complicated. It might have registry settings. It might have configuration files, etc. So packaged software typically is a bunch of files with some installation scripts and configuration files. For example, you know, on the Windows world, MSI files, DMG in the Mac worlds, RPM in the Red Hat, Fedora, CentOS, Rocky world, deb files in the Ubuntu, Debian space. And containers are just another way to deploy software, where they have a very specialized, their own format, and we're going to talk about that a little bit. And they're downloaded from container registries versus package managers like RPM files and deb files that go out to a registry, but not a container registry, a package registry specific to that file format. So why is software deployment a big deal? Why is it a big deal? Well, look, So you've got an application, a gigabyte application. A gigabyte's not that big anymore. I got to install it. So what? What's the big deal? It's not big these days. A gigabyte, I can wait for it to download. It's not that long to download a gigabyte these days. And hey, I'm only installing it once, so I shouldn't be thinking about deployment. And hey, I have more disk space than I'll ever need these days. I have 2 terabytes on my machine, but I do a lot of AI and ML stuff, so I need a lot of memory, a lot of disk. But big deal. What's the problem? Well, this is why it's a big deal on the enterprise stage. If you're organizationally, what if you need to install that 1 gigabyte application? And a gigabyte is not big these days. Like I said, SAS is 40 gigabytes. ML and AI applications are typically lower bound of 3 to 4 gigabytes. So what if I need to install a 1 gigabyte image onto 1,000 machines? Great. And maybe those machines are globally across the world at my various data centers or whatever. Or maybe or on the other extreme, I've got a compute cluster with 1,000 nodes, and I just got to blast that gigabyte application onto those 1,000 nodes in my compute cluster. So let's do a little math. 1,000 copies of 1 gigabyte is a terabyte. So before you can use those images on 1,000 machines, you have to send a terabyte over your network, and that makes your network very sad, especially if you want a smooth network. And what if you're running a cloud where you're paying for network charges? So the network cost adds up really quickly. And also, you can't start the applications anyway till they're downloaded. So, and it's not uncommon that applications are frequently updated. So it's not just the one-time hit. It's you may get. I know of some high-frequency training models that are updated many times an hour in the financial space. But it's not uncommon for applications to be updated pretty frequently these days. I might want to do fast startup. I mean, again, if this is a microservice I want to quickly spin up, if I've got to wait a couple minutes for the application to start, it's not so I'm not getting that agile startup that I want. And similarly, if you have an application that's auto scaling, you want it to auto scale when you need it, not a few minutes after you need it. Software deployment is an old problem. The general problem of software deployment, and I do a lot of enterprise work, and one of the things, if you've been around for a while, you'll learn that the big banks, are really software companies. They have really, really sophisticated software, tens of thousands of applications, hundreds. The big ones have hundreds of thousands of nodes. So the problem of software deployment was really clear all the way back in the 90s. So if you look at this Usenet paper in 1995 by Phil Moore from Morgan Stanley, and he was talking about a system that they designed in Morgan Stanley to deploy software throughout their plant and data centers around the world. It was based on the Andrew File system, AFS. And it wasn't just Morgan Stanley. Goldman Sachs did also, and many other organizations had to build their own homegrown ways to deploying applications, pre-containers. And so, here's a 2021 2021. And the banks are very proud of what they've done, and they let their engineers talk about it at conferences. And the LISA conference in 2021, a Goldman Sachs engineer gave a talk on leveraging AFS software to ease global software deployment. For example, and at the same moment a year later, give a talk of accelerating software distribution and execution at ever-increasing scales. Because again, they're distributing to hundreds of thousands of machines, but even if you're distributing to just a few hundred machines, it's still an issue. Even a handful of machines, it can be an issue if you need things fast starting. And they're looking forward to, and all of that was pre-containers. We're not talking about containerized distribution, we're talking about distribution in general, and they're not they're not looking at the future. So there's a talk on lifting and OpenShifting. OpenShift is if you don't know, is Red Hat's distribution of Kubernetes. How do you get similar deal with software distribution when you're moving to containerized solutions? So why did they? I just want to take a slight digression. Why did the banks hone in on the AFS family of file systems? Most of you are probably not familiar with it. It's been around for a long time. Great file system. File systems are, how do I get data distributed to the world? That's what a file system is. And you have a local file system. Under the / directory on your machine, there's directories and files, and that structure is called a file system structure. You can clone them together with, which is what called mounts. You mount one file system to another file system. That's how if you have multiple disks on a machine, you can do stuff like that. The AFS family is a distributed file system, namely, if you're getting your files from other computers like NFS, if you're probably more familiar with NFS, or Windows network shares and things like that. But the reason the banks focused on the AFS family file systems is two things. One, it has this beautiful cache consistency model that survives reboots. Unlike most distributed file systems, if something changes on the server, you don't know, and you have to poll the server. In the AFS family, the server has a lease with the clients, and the clients get told that something's changed. So it's got a wonderful class consistency model, but it's also really fits well into managing data and software, because it has a thing called a volume. And this volume is a policy container, security and high availability and all this nice stuff. And all a volume is a rooted directory tree. It's an entity in this AFS world that just really corresponds to a directory of stuff. And you can mount it anywhere in your local file system, for example. The global namespace, but I don't want to talk about that. This isn't a talk about AFS. But I just wanted to say that they found it interesting. The reason the banks found it interesting is what they did pre-containers is they had configuration management systems that would take a really, really tiny VM. Like what was in the VM was really small. And what they did is they sewed together a file system by mounting these directories of stuff and then starting their application. So, for example, the configuration management might say, oh, I want this version of Java. And so there would be a AFS volume with that version of Java that they would mount onto the system. And then the nice thing about distributed file systems is you only pull the content in as you use it. You're not installing. So for them, they were able to start their applications really, really fast. So the point I'm making is that the idea of needing fast loading, small chunks of code to deliver over your network for deploying application is an important problem. It's an old problem, and again, the banks have been focusing on this for a very long time, among other issues. So, what do I mean by enterprise software? That there's why does an enterprise care? And again, this is not just an enterprise talk. If you're doing any AI/ML where you're running something on a couple hundred nodes, or even a couple of tens of nodes, or a couple thousand nodes, what are you doing? And you deploy applications. Some are infrequently updated, long-running applications like a database. Some are frequently updated applications like a high-frequency trading model or any AI/ML model. It could be short-lived microservices that you want to start quickly and tear down. There's lots of different applications in the world. Now, how many applications are running on a node is another question. In the containerized world, it's not unlikely either using Docker directly or using Kubernetes, or if you're in the Red Hat world. I tend to focus on the Red Hat world because that's what most enterprises use. You might be running tens or hundreds of applications on a single node. Or whether it's running them directly with Docker or running via Kubernetes. But then the other question is, how many nodes you have? Again, you might have hundreds or tens of thousands of data nodes spanning multiple data centers in a hybrid multi-cloud across multiple regions. Or again, you might have a lot of nodes in your HPC compute cluster. And as I said earlier, size of containers can be a couple megabytes, but they can also be tens of gigabytes. For example, AI/ML applications tend to be at least 4 or 5, 3, 4, 5, 6. It depends on what you're basing it on, but they're not small. They're not small. So now let's talk about containers. I want to now I'm going to get into the geeky stuff. Containers work by leveraging some Linux capabilities. There's something called, like I said, namespaces, protect the user IDs, the process IDs, the network IDs, C groups control, allow a single machine to dole out memory, CPU, and IO, etc. But the thing I really want to focus on is the container root file system. The container root file system is when you run a container, you're seeing slash and downward, and that directory of files you're seeing in that running container are not actually the directory that you're seeing on your host computer, because that would be very bad. That would be a security breach. And by the way, you wouldn't have been deployed your software. The deployed software is in that containerized root file system. So there's two things to focus on. Two things that have been over the years developed in Linux to handle that root file system. Something called overlay file systems and something called Chroot. So what's an overlay file system? Some of you may know this, but I really want you to kind of get a deeper understanding. What that is it's a synthetic directory. It's a directory that doesn't actually have files, but looks like it has files. It looks like it has a directory of stuff, and it's made by a merging of multiple other directories. So if I have a directory here with a version of file 4 and file 5, and a directory here with a version of file 2, file 3, file 4. Those are the file names, by the way. And here with a version of file 1 and file 3, and maybe I had a version of file 5 there, but I deleted it. What an overlay file system would do is say, I want to create a synthetic directory that's a merging of all of these, kind of like overriding in an object-oriented file system, programming language, where it just, like, if these were subclasses, if I called a function, file 1, I'd see this file, even though it's not in the first layer. If I and I asked it, look for the file, it'll find it in the second layer. If I have 1 and 3, one in layer 1 and layer 3, it'll find the topmost one, this one. Similarly, if I have 1 in layer 2 and 4, 2 and 3, it would find the 1 and 2, not the 1 and 3. Where an overlay file system is different than just straight overwriting, as an analogy, is if I had the file in layer 5 and deleted it, it would be missing. There's a way to signify that a file has been deleted from a layer. We'll go into that later. And what it does is this synthetic file system will get all the files from these lower layers as read-only files, and it'll have another layer that starts out empty, that is the read-write layer. And any file you add or any file you change will live in this top layer, and that will be what it sees. So, for example, if I created a file 6, logically, if I kind of CD'd into that synthetic directory and I created a file 6, it'll appear as it's in that synthetic directory, but it really is creating it in this read-write layer that the overlay file system uses. If I delete a file, I want to see it missing, and the way it knows it's missing is it does put something special in that read-write layer. We'll talk about that in a second, etc. So now let's go to a demo. I have way too many windows open. Here we go. There we go. All right. So let me give an overlay demo. So what I'm going to do over here is I'm going to in this window I'm going to run just a just a script that's watching this directory, this temp overlay fs directory. So now let's run our overlay, that overlay fs demo that I just mentioned. I'll make it a little bit bigger. So we want to create those layers that I just mentioned. So I just wrote a script that created these files. Have directories named layer 1, layer 2, layer 3. I just created some files in them. And the one file 1 has hello file 1 from layer 1. File 3 says hello file 3 from layer 1. There's another version of hello on layer 2 that says hello file 3 from layer 2. So you see what's going on there. So now let's, if you want to, this is something that containers use that you should understand, is the overlay file system. If you want to create one, first you have to create the target for your synthetic directory. So I just created this directory here, this synthetic target directory. Make it a little bit bigger still. And now what I'm going to do is I'm going to create that read-write upper directory. Again, you have to create a directory and say, hey, overlay file system, I'm going to want to use this. So now we're done setting things up. And let's go ahead and run this command. I didn't run it yet, but I'm going to run this command. This is the magic command that internally or implicitly or explicitly all your container runtimes will use, something called fuse overlay fs. So this big long command that has a -o, lower dir equals, upper dir equals, blah, blah, blah. The last parameter is the target, the synthetic target. But let's just, what I just did is I just broke that down. I just did some grep magic. And what I'm saying is I want to create a synthetic directory called synthetic target that's going to be created by layer 1 sitting on top of layer 2, sitting on top of layer 3. I told it that's where my read-write layer. So now let's actually run it. So look over here. Let's focus on the synthetic target. I'm going to now execute that command. And look at this. Lo and behold, it has those 4 files as I said. You know, this is the end result of what I did there. You know, that's the merging, as I said. And if you don't believe me, I printed in that synthetic directory file 1. It's the one that was in layer 1. File 2, which is the one from layer 2, correct. File 3 is the one from layer 1, correct. And file 4 is the one from layer 1 as well. Layer 2 as well. Layer 2. Okay, so it worked. Yay. So I now have this synthetic directory. Now, what happens again if we create a file? I'm about to create this file 6. Again, watch over here, and there it is. It appeared in file 6, and just as I said, it's not just in file 6, it's also in that read-write upper layer. So this is how the mechanisms work, and containers use this. So there, I'm seeing the files, and in fact, from my synthetic directory, I'm seeing the file that I created in the synthetic directory with that name. And if I look in the upper directory, there it is as well. So just what I said in a moment ago, but this is sort of in a demo. And the last thing I want to do is show what happens if I delete that file 2. I deleted file 2. I ran it too quickly. I deleted file 2, and it's gone now. It was there a second ago. It's gone. But look at it. There it is in the upper directory. Well, that's interesting. Remember I said that when you delete a file, the upper directory has kind of a version in it? Well, the way it works is this. If I try and look at the files in the upper directory, I get an error on file 2, permission denied. It's there, but I don't have rights to look at it. So let's see what's really going on and do an ls-l. And we see that in that upper directory, the file 2 is there. It has no read, write, or execute permissions at all, but it's set up as a character device. And that's how overlay file systems kind of indicate that file 2 was deleted. File 2 was deleted. So that indication that it was deleted is in the upper directory, and it is not then the synthetic target knows not to show it. So that's my overlay FS demo. Now I want to talk about this thing called Chroot. All of this is, be very clear, all of this is under the directory temp overlay FS. There's nothing magic going on there. It's just a regular directory. So now let me go ahead and run a different demo. a different demo, Chroot demo. And again, here I'm looking at a different directory. This is just tree, watching the tree. So now let's run that Chroot demo. And I created a synthetic root, which is a created directory. And what I'm doing is I made a directory bin, and I copied from my local machine bin bash ls echo cat tree and bin. So I have the binaries for those programs right here. For those of you who know about dynamic dynamic libraries like CLib, etc., these programs are dependent on some libraries. And there's a program LDD, which if you ever want to know what libraries a particular program is dependent on, you run LDD, and it says that, okay, bash and ls, bash is dependent on this library that's there, and I said libc, and it's dependent on libc. Ls is dependent on also libc CRE. So you see, it's got a bunch of dependencies. So what I'm going to do is I'm just going to copy the dependencies. So all I did there was I copied all the dependent libraries that they were all in the directory /lib64 on your local machine. I copied them into that directory. So now I have a directory synth root that has a bunch of files, but it's a file on my system. I can, it's just ls there. But now I'm going to run this magic command called Chroot. Notice what happened. A minute ago, I was on my machine. Now I'm on. It looks like I'm on a different computer. I didn't actually log into a different computer. I just said I want to start a shell in a clean system that doesn't have my home directory, my root directory, but it has the other guy's root directory. So if I do ls, ls/, I don't see the files on my computer. I just see this in this synthetic directory. And I can go, ls-l bin, I can do tree. I see the files, but notice they're just under here. Same files under here, but it looks like it's under the root. And I can do, cat echo hello to out. There's out, right? Nothing special. Now let me remove out, and it says command not found. The reason it didn't work, I don't have my whole system. I just have these few programs, because that's all that's in this root. So this is an important thing. So we'll see that when you run a container, that's what's going on. That's how your root file system gets created. I'm going to exit and go back here. And oh, I forgot to create files. Oh, well. I was supposed to create some files, but they didn't. I was supposed to create a file called hello and goodbye, but I didn't do that. Oh no, I did. I'm sorry. I just created these two files, hello and goodbye, in. No, I didn't. Make dir temp to root data. Oh, I did create a data directory. Oh, I know why. I have, because I have that selected. It's not refreshing. So there I have a data directory. I created two files, and now cat data, cd data, ls cat hi world, cat by world. So I can put files. I can put data files. I don't just have to put binaries. And this is not this is a bind mount. I'm not going to go into that because it's already taking more time than I want. Okay, so let's go back to the demo, and So, for those of you who are familiar with the the Linux Foundation, you should be aware of there's something called the Open Container Initiative, and that's the governing board that says what is the official legal, supported structure, of a container image, and how should a container runtime work. So if you want, anybody can write their own container runtime. It doesn't have to be Docker, but you better be able to support container images in that format. And under the Cloud Native Computing Foundation, which is another big group, there are two projects with container runtimes. One is Container D, and the other is Cryo. That Container D is basically Docker, and Cryo is basically Podman, which is also and the container runtime that's used by OpenShift. Red Hat's OpenShift. Podman and Docker command line are almost identical. They just have different implementations of the container runtime. So it's a repeat slide. So what's really going on? What really is a container image? A container image is something that contains a manifest with a list of layers that are used by that container, and those a way to get that. So it contains the manifest, and it contains a set of files which correspond to the layers, and they tend to be stored as compressed tar.gz files. And these images are typically built in your CI/CD pipeline or your Docker build, and then you push it to your container registry again in your CI/CD system, and you push it to a host / repository / tag. For those of you who aren't familiar with containers, it's a little confusing. Repository is really the name of the container, and tag is the version. So I don't love the name. So this is called the registry name, the repository name, and the tag. So here you have the container is a manifest with a list of named layers, and then list of ID'd layers, and there's the list of the files. And so what really goes on is when you build your container image, you have a bunch of files and layers. They're files. They're files. They're real directories. We'll see that in a second. And when you say push, it compresses, it sends up a manifest describing them, and it compresses the files and throws them onto your container registry where it stores it locally. When you say pull, it grabs them down one at a time, and it grabs the layers and unpacks them into directories. And again, so what's really going on is, again, I'm saying Podman, but it could be Docker run. The first thing that it does is it goes to the registry and says, hey, I'm sorry, I left out an important point. Container registries are really object stores. Everything is actually really an object store. Your local file system is really an object store. Once it's done the name resolution, namely from the path, internally your file system does everything with an object store, not with an ID. So an object store just ID data, a server that can give it an ID, give me the data corresponding to that ID. So in the container registry, when you want to pull an image or run an image, it first goes to the registry and says, hey, this is the name of the image that I'm looking for, and it gives back the object ID, the digest ID of that manifest. So you don't actually, when you first give it from the name, you don't get the manifest. You get a digest, and then your container runtime has to again go, hey, here's the digest, give me back the manifest. And then it looks at the manifest and sees the list of the files and the digest of all the layers. And then for each layer, it says, hey, give me this layer. It gives back a blob as a tar.gz file, and it extends it to local disk. All right. So, hey, container build demo. So another demo. Docker demo. Docker demo. So a Docker file is kind of like in terms of the files are concerned, kind of is like building a layer. So here I'm saying, here's a Docker file that says from Alpine, which is a small Linux version. Create a file in layer 3, hello file 4 from layer 3, hello file 5 from layer 3. This is identical to the previous example, but I'm doing them in Docker layers. Then I say I want to build a container a container Larry based on that container Mo that I just created up here. And I want to then, from whatever files were in Mo, create a few more files. And then finally, there's layer 1, where I say from Larry, create a container image curly that has everything that was in Larry, but now I'm going to create a few more files. And I'm going to remove file 5. This is exactly mimicking what I did with by hand with the overlay file system. So now let's build them and push them to a registry. So I just did that. Great. Now let's run the images. So I'm going to say podman is named docker run mo. And I go and look, there's layer 4 and layer 5. Remember, Mo had file 4 and file 5. Mo had just file 4 and file 5. Right? Now let's look at Larry. And again, Larry extended upon Mo. And created a few more files. And there they are. And if I look at the contents of layer 5, file 5 is there. If I look at cat file 4, you'll see that I have the image from layer 2, not the image from layer 4. And finally, let's run the image curly. And there I see, again, going back to what I did before, just going quickly, I was just emulating what I did this, and I'm going to just see the files in this structure where the bottom one is Mo, the middle one would be the container corresponding to Larry, the top one would be the container corresponding to curly. And so if I cat file 1, I'm going to see the version from file 1. I cat file 2, I'm going to see the version from file 2. I see cat file 3, I see the version from file 2, layer 2 as well. Again, right? And cat file 4, it's there, and cat file 5, it's not there because it was deleted when I built that container. So there you go. So what's really went on under the covers is the Docker runtime grabbed those layers from the container registry and then used those to create an overlay file system. And then when it started your container, it Chrooted it into it so that you only saw the files in that container. Got it? So there's where the combination of overlay FS and Chroot come together. All right, so now I just pushed it to a container registry because I'm going to want to use it in my next demo. So all I did is I pushed it to the container registry. So going all right, we'll go back to that in a second. So what are the jobs of container runtime? Its job is, when you say pull an image, you pull it and then run. Its job is to grab the images and put them on your local disk. And when it's time to run, it takes those files to create a synthetic file system for the root of your running container. Where those files are stored is vary from Docker, which stores it here if you're running rooted Docker, and Podman, if you're running rootless Podman, which you don't need to be super user, it stores them there. So let me do my container demo now. My container demo, local disk format demo. I am running out of time. I apologize if I go over. Okay. So again, same idea. Now I'm looking at a file temp Scopio. Scopio is a program that is not a container registry. It's not a container runtime, but it knows the protocol for downloading the files. So what I'm going to do is in my run the Scopio demo, I'm going to run this command Scopio copy from the Docker registry curly the files into that temporary file. So notice that it just copied a bunch of files. In fact, there's the manifest, right? So let's look at that manifest for a second. Again, it's just a file. And if we notice under the file, there's an array of there's a configuration section, which we'll talk about briefly in a second. And there is the list of layers. And again, everything's done as an object store, so the layers have object IDs. Okay, so all it did was the way Scopia works is it first goes to the registry, with the name, gets back the object ID of the manifest, gave the object ID of the manifest, downloaded that manifest.json file, and then looked at the manifest.json file, and for each of the layers and for the configuration file, it downloaded the blobs corresponding to them. So I just did a little, this is just jQuery if you're familiar. I just pulled out this is extracted from this above. That's the actual IDs of all the layers in the order that they are requested. And so let's look at the file tar. They're a tar.gz file. So I'm going to just run tar.xfs blah 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 blah. That file, because that was my layer 1, my top layer, right? My bottom layer, actually. It's my bottom layer. It's the reverse order. And there I see the files that were in Alpine, right? So now I'm going to look at the contents of this second one, 6D. And there I see the files from Mo, when I built the Mo container, because that's what it does. It builds a layer each time you do container build. Then here's the layer corresponding to Larry. And here's the layer corresponding to Mo, the topmost layer. Notice this weird file, this .whiteout file. If you remember, I was talking about the container, these guys here. This guy here. They said if you want to indicate in a tar file corresponding to a layer that a file has been deleted, rather than putting a file with that name, put a file .wh and that file name. So that's one of the standards of the container images. So that's called a whiteout file. All right, and that if we went back up and saw the configuration file, was the file F3 something something something. You know, there it is, right? And I'm going to just look at the configuration file, and we see in the configuration file a bunch of stuff. Oh no, this is the manifest. Sorry, this is the manifest which said the configuration of file is F3, and this is F3, the file F3. And notice that it has the environment variables that were set when I used that when that container was built, because you remember I said that you need configuration as well, and it even actually tells you a history of what were the commands used to generate each of the layers in the history. Okay, got it? So there you go. That's the end of that demo. So now we're masters of how to build the container file system for the container runtime. So now let's go back to our presentation. And so again, important things to understand. This is a repeating slide, that all the layers have to be downloaded before and expanded. tar.gz files have to be expanded onto your local disk before your container images can start. And again, remember, these could be very big containers. They may take up a lot of disk space. So if I'm running, for example, a Kubernetes cluster with 100 different containers running on it, that may take up hundreds of gigabytes of local disk on my node, and I may not have that much disk on my node to run my applications, for example. You know, because ultimately your applications need data space as well. All right, and again, I talked about the network load. Downloading 1,000 gigabyte applications is a terabyte over the network. So quantifying this, if I'm downloading one node onto one application and the image size is 1 gigabyte, it's going to be a gigabyte over the network and 1.5 approximately gigabytes on your disk, because a compressed file gets bigger when you uncompress it, for a total size of 1.5. But if I do it to 1,000 machines, that one app, I'm moving a terabyte over my network, and the total disk space spread over my 1,000 machines is 1.5 terabytes. It's 1.5 gigabytes for each machine, but 1.5 total over my 1,000 machines. If I'm downloading 100 applications onto one machine, again, I'm 100 gigabytes over the network, 50 gigabytes on my local disk. And if I download that 1,000 applications to 100 machines, I'm moving 100 terabytes over my network and using 150 gigabytes on each machine for a total of 150 terabytes spread over the many machines. It's a shitload, excuse my language. So an important observation was made several years ago at a conference in 2016. They did an analysis of all these different container images, and a group from the University of Wisconsin, down here is the link and the article, goes fast distribution of containers. They said they did a proof of concept related to some of the things I'm going to talk about. And what they know, the walk away is pulling packages. When you're starting a container, the pulling of the packages accounts for 76% of the container's start time, but only 6.4% of the files on average is actually used, the coverage, when you run your container. So only a small percentage, that's the important observation, only a small percentage is actually used, even though I have to download it and compress the whole thing. So again, putting that into numbers, if we believe they're 6.4%, my one downloading if I only were able to download the files I needed, I would only need 64 megabytes, not a gigabyte over my network, and I would only need about 96 megabytes on my machine, right? Ditto, 1,000 nodes. This should have been this should have been 6.4. Sorry, this would be 640 megabytes. Less than a terabyte instead of 1,000. No, this should have been 6.4 gigabytes. That's a typo. If I was doing 1,000 nodes, this should have been 6.4. Running one application to 100 machines would be 6.4 gigabytes over the network. Bottom line is, I'm reducing my network load, and I'm reducing my local disk requirement, and I'm reducing my total disk requirement over all the nodes, if I can truly just download the files I need. So is it possible to make files directly accessible without doing the pull, without downloading that layer blob? Again, we don't need all those files in the container. It would be great if we could just download the files that we need. Now, just to give you some insight into what's going on over here is Docker. When you pull an image, to reiterate what I'm saying, if you look at under this directory /var/lib/docker, you'll see all the files in each layer. I just have one layer here, but you see all the files in the layer are explicitly untarred at this place in the directory. If you're using Podman, it's in a different location. And something to bear in mind is Docker maintains a whole structure and database of all the container images it's downloaded and all the containers are running. That's one implementation of a container runtime. You'll see there's a completely different rearrangement, a completely different set of databases that Podman uses. It's just a different implementation, but nothing different in that they both would need to ultimately download the files locally. Now, if I could do something like put this on some other way, if I want to, what are other ways? Again, what can we do without doing a poll? There's two different approaches to how to solve this problem. One is with an additional image store, which is basically it makes you can have more than one of these data structures. This is the one that you have. But if you were using standard plugins to Docker, you could have multiple ones, and so would look for the image and you'd get a list of these data structures. It wouldn't be one; it would be many of these, and it would look for in the database of the first structure for your image. It would then look in the second one, and so you create a list of full structures of that complex data format and database format. And just jumping ahead to the punchline, and you would do that because you might have on maybe an NFS share a copy of a Docker database, not so much for the running containers. The running containers have to go locally, but the images are over there. So I could just pull the images over there. And so these would still be files. They would still be expanded. They would still take up the full space, but they'd be living, for example, on an NFS share. Okay. And then when your container runs, it's just pulling in the files that it needs. There's another approach called additional layer stores, image store versus layer store. So rather than creating an alternate way to get everything about the image with all additional layer store, it's just a way to get alternate versions of the contents of a single layer, of each layer. Again, additional image store, you're copying the whole structure. Dan Walsh in 2020, I think 2019, 2020. Dan Walsh is like Mr. Podman. He's like the container guy. Super smart guy. He wrote an article, if you want to find it, on something that you could do with Podman and additional image stores. On the Docker front, I don't know of a general solution or a generally available solution. The only one I know about was a Google engineer at the last KubeCon gave a talk reducing AI jobs cold start time from 15 minutes to 1 minute, which is exactly if you look at what I just said, it's exactly what we're doing here, what I've described here. If you want to see his version of this type of stuff, you could find that KubeCon talk. But that's a Google solution, and when pressed, he said that it was going to be proprietary inside of Google, and it was ambiguous when it was going to be available. He said April. I don't think it's available yet. So if you want to look at that talk or that article, you can read about all additional image store approaches. Additional layer stores are where you're just replacing the layers. I'm going to go over, I apologize. There's, again, plugin capabilities inside of Docker's runtime, Containerd. It's called snapshotters. There's a plugin capability inside of Podman called additional layer stores. There are implementations, some of which are publicly available, of StarGZ, IPFS, where they're backing the layers. Here's just a screenshot from the GitHub page of StarGZ. This RSR container accelerator is what I've been working on. So again, what we're trying to do is how do I get away without downloading the entire container? So let me go to my last tranche of demos before we wrap up. All right, change some layers. Okay, so for this series of demos, I just want to say I have some scripts, like SDI is a script, but what it's really just doing is container. Here, I'll just show what happens for all the scripts I use. I use my own commands, but I echo what's really going on. So this is just container images. All right. So I'm gonna get rid of everything on my. Those are the images that have already been downloaded, and so now this done. So I've wiped out all the images that were local on my machine. They're gone. All right. So RMI. So now, and so I want to use some invariant variables. So source set demo images. I just have some environment variables set. Curly is the guy we built a little while ago. It's about 8 megabytes in size. That's where it is on the registry. Something called small Python, which is the standard reference Python, which is a gigabyte. And then I have a big image of mine that's 5 gigabytes. All right, so I'm going to use these images. So again, I'm using one of my magic scripts, DRQ. Small echo hello. Oh, I left something out. I left an important thing out. I'm gonna remove. Okay, I've got an empty image. I'm gonna want to run over here. Is watch over here. So I just flushed the cache. So what you're seeing here is that under that directory, that containers directory that I said, I'm using Podman. Podman's staring its images. It's only 208K. When I clean it out, it's just got a bunch of, its own work files, and it's only 108K. I've cleaned out the Orster cache, so I'm being honest and saying we'll see what's actually coming over the network into the Orster cache. So now if I do the following, so now let's go back over here. So I'm going to say run that small image echo hello. And notice what happens over here. This went to 8.9 gigabytes because when I said podman run, it had to do a pull, and it pulled down that small image. And it took a gigabyte, 8.9 gigabytes of real local space on my system using standard Podman or Docker. So and if I look over here, there it is. So Docker images, there it is. But that's not interesting. Let's do something a little bit more testing. Let's run let's run that Python. And what I want to do is run the command Python -C. For those of you familiar with running things on command line with Python, print hello from Python. Okay, and I'm going to timestamp it to see how long it takes. So now what I'm doing is I'm running, and look at what's going on here. It's downloading Python, and there it goes. As it untars those files locally, this grows. Right? Just proving out what I said, that Python, takes a lot of disk space. Right? It's still downloading, it's still untarring, so it ended up downloading 1.4 gigabytes of files onto this directory. It took 22 seconds to start, and it used 3.1 CPU seconds. So it actually used a half a minute of my CPUs, because I have more than one CPU. It probably parallelized the untarring. And lo and behold, there it says hello from Python. Right? So it really did run. All right. So, and if I go, Docker images, Podman images, there you go. There's Python, and it is in fact 2 gigabytes. So let me now go back to the. I'm going to remove Python. We'll see this will shrink down to that 8.9, and then I'm going to remove my small image, and it'll go back. Oopsie. 208K. right? Kind of the empty one. So I'm going to start the demo again, but now I want to do it running the Orastore container accelerator, which is one of those additional layer storage um, uh, uh, capabilities. So I'm going to just over here, bin ACA, and it's running a program. Great. So looking over here, so now I'm going to do exactly what I did before. I'm going to do exactly what I did before. Oh, sorry. I first want to show the configuration file. You'll notice that to activate it, all that I did was I said, hey, remember I said you give it an alternate place to look for layers. Hey, Podman, when you run, you might also first look to see if you can find your layers there at this directory. And lo and behold, that's where my container runtime is presenting files. It's dealing with something called a fused file system. I don't want to talk about that, but it's doing some magic that it's going to look for the files under this directory. It's telling Podman you might want to look for the files in this directory. So now let's do drq my small image. All right, great. It ran super fast, but instead this went from 208 to 280K. 280K. Wait, before it was a million. 8.9 million, right? And if I look at if I say, hey, Podman, what's going on? It thinks it has 7.6 files available to it to run this container, available to it. What's really going on is when I ran that program, what happened was, if we look over here, the files were in fact brought over the network onto the machine, but they were done by the Orastore file system. And it used 1.5 1 gigabyte blocks. So it downloaded 1.5 megabytes over the network, not 8 megabytes. Okay. And if you look over here, the reason what was happening is, this is my fused file system. When Podman looked for the layer corresponding to this digest, it's providing the content indirectly from one of the volumes in, remember I started a volume, which is a rooted directory tree, for one of the volumes that has been stored, that's living in the Orastore file system. So, but okay, let's do the same, the Python test, right? The same one. And again, watch here. This started out with 1.1500. Now run that. Look what's going on here. Whoa! This only went up by 100K, 101 or 200K. Instead of taking 22 seconds, it ran in 4 seconds. Remember we said the start time drops by 76%. It only used 0.15 of my CPU, so it took much less clock time and much less CPU time. And instead of downloading a gigabyte, it downloaded, again, 1600 times 1K is 16 megabytes. 16 megabytes of that 1 gigabyte container image. So there we see that the coverage of running Podman hello, print Podman hello, it really ran. The actual file coverage was only 17 megs, even though without this, you would have had to download the entire 1 gigabyte. I realize I'm way over time, but let me do two more quick demos, and we'll see that. So now let me do the following demo. Let me now say, well, let's try and run curly, that curly that we had run, right? Now it ran, but wait a second, 9.2 megabytes. Why? Why didn't I get the benefit? Why didn't I get the benefit of curly? And the reason I didn't was that there wasn't, if you look over here, there wasn't an Aura store volume corresponding to this digest ID. So when the container accelerator was asked to give the files, it said, I can't. There's no underlying, there doesn't exist a layer volume for it. So what you would need to do is generate that. So that's this other program called the layer volume generation service. I'm going to just start that over here. And all I have to do to make it a volume available is go, so let me remove the version, the 9.2 version. Bring it back to its base. I'm now going to, over here, I'm going to say, I want to, hey, layer volume generation service, I would like you to, could you please ingest curly to be optimized? And looking at this bottom screen, what happens is it goes to the layer volume generation service and it's processing all the layers for curly. It's now available. So I can now say, if I go back and do that, run curly, it runs, boom, runs super fast, but it only brought another 100K over, used a couple of 100K. So it used very, very little. So there's my complete demo that of this. So wrapping up. There's two approaches: additional image stores, which has the flaws that you have to pre-build them for multiple machines, which means you have some potential conflict issues and update issues, and it's more heavyweight. Versus image stores, where you're just layer stores where you're just providing the files of the layers, not the whole image structure of the container runtime. The way StarGZ works is they require, this is an open source project, you can play with it. They require sort of pre-rebuilding your container images. And into a special format, a non-standard format, but it can be used by a standard container runtime. And they lazy load the tar files and do some unzipping of just little pieces of the file, and that's why they need that little pre-step to make the layer volumes in a format that you can, because you can't cherry pick files out of a tar.gz file. Per se, you have to do some magic. So that's what StarGZ does. There's another implementation using the same tech. And I'm sorry. So and StarGZ, all of these have versions that work either with Docker's Snapshotter or with Podman's additional layer store. But the StarGZ is lazy loading from files. IPFS is lazy loading from files in the I forget what IPFS, Internet, the blockchain file system, IPFS, and the Aura Container Accelerator I just showed you does it by using mounted volumes from the Aura Store file system. So that's how it works. This is Aura Store specific. I'm not going to waste time on, that's how, you generate files. I gave that one example where I generated the volumes for curly, and it's designed as an enterprise product, so it will then geo deploy your container images around the world for fast loading, and has all this high availability and redundancy, but it gets all of that because of the underlying Aura Store file system. So there you go. My one sales pitch is, the Aura Store Container Accelerator works with any container registry, any container image, any container runtime, gives you faster start times, reduced local storage requirements, reduced network traffic, and better tools for safe container lifecycle management. I apologize for going 15 minutes over. I apologize for my little sales pitch. I did use Orester Container Registry as an example, the Orester Container Accelerator as an example for how to get fast start times. And I pointed to some other ones. If you're interested in this, reach out to me. I'm done with my sales pitch. This was a great opportunity. Apologizing again for going 15 minutes over. Arden is a great company for both training and consulting services. So if you're interested in that, definitely please look at them. If you like my talk, I've done Docker container and Kubernetes talks with them. So if you want one of those, you might get me. Anyway, that's all. And thank you again for listening to this talk. I'm Jerry Seidman, and that's how to get me at Orester. I have an Arden email account, but I forgot to put it on here, so let's just use that one. Okay, but reach out to Arden. They're great. Okay, thank you, everybody.